The parent functions that we're going to talk about today will serve as a basis for a lot of discussion that we have coming up with how functions are manipulated. So, parent functions are the basic functions that you use to then create more complicated functions. Basically, you are building families of functions based off of these general shapes. So, to start, we have 8 parent functions that you will be responsible for. Those are the ones listed in blue. A lot of these you've seen. You might not realize that they were called parent functions, but they have a general shape about them that is important and can be stretched or reflected, altered in some way. The ones listed in red, sine, cosine, exponential, natural logarithmic, and the logistic curve, are parent functions as well, and you will use those later in the course. But for right now, you are responsible for the 8 that are listed in blue. Here's how we represent each one of those parent functions as an equation. You've seen a lot of these things before. I'd like for you to take note that all of these involve x. You're not multiplying, you're not adding, subtracting, really you're not altering them in any way. You are just performing one function on some variable x. So you've seen all of these before. We're going to talk about them a little more in depth and for what you are responsible for knowing. First one we're going to talk about is the constant function. Constant function is just that, it's constant. It's neither increasing nor decreasing. Its domain is going to be all real numbers. So you can put in anything you want, but you will always get back the same value. So your range is just whatever your constant value is. So let's say this was going through at, we'll say 3. This would be the constant function f of x equals 3. Because no matter what x value you put in, you are constantly getting back the number 3. So in this case, our range would be 3. Next one we're going to talk about is your linear function. Again, this is just f of x equals x. So our domain, our x values we can put in anything we want. X could be anything. Our range that we get back out, I'm going to do this in a different color, will be all real numbers. If you put in any real number, you're going to get back any real number. If I put in 1, I'm going to get back 1. If I put in negative 500, I'm going to get back negative 500, etc. Linear function. We've done a lot of work with linears in previous courses, and we're going to review some of that right now. So, different ways to write linear functions. The first one is slope-intercept form. In this case, the slope is represented with an m, and the intercept, in which case this is the y-intercept, is represented with a b. So, in order to use this equation, you would want to know the slope, and you would want to know the y-intercept. This is the form that you are most used to seeing, especially when it comes to graphing, because it's an easy way to graph a linear function knowing the y-intercept and then count your slope, connect the 2 dots, and you're done. The next one is point-slope form, and that's going to be y minus y1 equals m times x minus x1. In this case, the point is x1 comma y1. So you will be given some sort of a point, or you'll be able to find it from a graph. And your slope is still right there, represented as m. The last equation that you should remember, since both of these things involve slope, is how to actually find slope. So slope, as a reminder, is your change in your y values over your change in your x values. So it's rise over run, how much you go up versus how much you go over, etc. So y2 minus y1 equals x2 minus x1 is equal to m. As a side note, I'd like for you to look at this equation, pause the video, and think about how it might relate to this equation. Alright, hopefully you paused. What you'll notice is if I just multiply both sides, I get this same equation. Now, yes, I have x2 and I have y2, but since those are just talking about various x and y values, it could be viewed as the same equation. So that's where we're getting that structure from for point-slope form. writing a linear function given two values. So first thing you need to do is figure out your 2 points that you have based off of your given information. So thinking about inputs and outputs, we basically have 2 points given to us, and we would like to write a linear equation. Well, if we were given 2 points, the easiest thing to me, I think, would be to find the slope. So let's start talking about that first. y2 and y1, does not matter which one you call which. I'm going to say -1 minus 12 over 16 minus a -10. -1 minus -12 is going to be -13. 16 plus 10 is going to be 26, which leaves us with a -1/2 slope. Well, now we know the slope. We also have 2 points that we can pick from. It does not matter which one. So if we write this in point slope form, I'm going to use this right here, y minus y1 equals our slope times x minus x1. Now, being good mathematicians, you should simplify a little bit. These numbers are going to work out pretty nicely. I'm going to add this 12 to the other side, so that's going to be plus 7. Now, the only advantage in writing it in mx plus b form is really just to graph it. I personally would be okay with leaving it in this form right here. Point slope form is an acceptable form of a line. It's also going to be the most important form in calculus, so keep that in mind. Same thing, I'm going to ask you to pause your video and go ahead and try this one, and I'll reveal the answer in just a minute. Alright, looking at what we have, we've been given 2 different points. I went ahead and found the slope of positive 1/3. Using the point 2, 4, I would come up with this equation. Using the point -1, 3, I would come up with this equation, which I then just simplified this minus and minus to make a positive 1. I would be okay if you left it in either one of these forms. Now, if you actually go through and you distribute your 1/3, add your 4, distribute your 1/3, add your 3, you'll find that you get the same line. That same line ends up being y equals 1/3 x plus 10/3 for graphing purposes. So again, you need to find the slope, and you need a point. Well, you've got 2 different points you can pick from. It does not matter which one you use. You're going to end up with the same linear equation at the end. Moving on to quadratics, another parent function that you have seen before. Our domain for our quadratic parent function is -∞ to infinity. You can square any number that you want. But when you square numbers, you are only going to get back positive numbers or 0. So we would write that as, that should be inclusive, 0 to infinity. Things that you should know about quadratic, domain and range for sure, makes our nice parabolic shape. This quadratic, as a parent function, is centered at 0, 0. You can go over 1, up 1, and over 2, up 4 to help you in graphing. Because it has symmetry, -1, up 1, -2, up 4. Cubic function, x to the 3rd. You can take any number and multiply it by itself 3 times over. And when you do that, even with negatives, you're going to get back all of your values. Sometimes people refer to this as a squiggle. Some people call it a disco man, if you think about his arms dancing. Regardless, though, your domain is all reals, and your range is going to be all reals. Absolute value graph, very important one. Your domain here, you can take the absolute value of any number that you want. You can tell we've got a lot of all reals happening. But when you take the absolute value of any number, positive, negative, or 0, you will only get back all of those positive numbers. Remember, absolute value deals with distance. So if you think about walking, you can only walk positive numbers. Similar to a quadratic, you've got 0, 0. You can go over 1, up 1. This time you'll go over 2, up 2. Over 1, up 1. -2, positive 2. Because when you take the absolute value, you get that positive number back. Absolute value has the shape of a V. The reciprocal function is one that starts getting a little bit more intricate with its different features. Our domain for this graph, we're dividing here, and if you remember we said we cannot divide by 0. So we have to say what makes the bottom 0. Can't happen. Well, that right there tells us our domain. Our domain is going to be any number we want, except we have to skip over 0. And if you look from left to right here, you can plug in anything you want, except when you try to plug in 0, there's an asymptote. Cannot do it. Our range for this graph, if we look from the bottom to the top, you can get back any number, except you won't get back 0. Now, the reasoning for that is a little bit different than the domain. If you think about it, this value right here is saying we're setting this equal to 0, right? Our whole concept of an x-intercept or a root. Well, if I try to solve that, I'm going to multiply both sides by x. 0 equals 1. Is that true? Not in my world, and hopefully not in yours. So that's why in our range we have to skip over 0, because our numerator won't ever be equal to 0. Square root function, we said whatever is under here has to be positive or 0, because you cannot take the square root of a negative and get a real answer. So our domain is going to be 0 to infinity, which also makes sense because you can't plug in negatives. You don't get anything back on your graph. When you take the square root of 0 or a positive number, you get back 0 and positive numbers. Some people refer to this graph as the swimmer's arm. Think about it that way. The greatest integer function is one that's a little bit tricky to think about. It looks kind of funny, but if you actually think about its purposes, it has some real-life applications for when you can put in any number, but you only get back whole numbers. So if you think about the concept that you can't have part of a person or part of a ladybug or part of ticket sales, that's where greatest integer function can come in handy. So you can put in anything you want, but you will only get back the integers, nothing in between. Here's a graph of sine of x and cosine of x. Sometimes we refer to sine of x as a mountain graph. You start and climb the mountain. Cosine of x, you're going to call it a valley graph, because you start and go down to the valley. Now, these are two graphs that we will look at in much more detail when we get into our trigonometry unit. For now, I just want you to have seen them as parent functions. Likewise, we have our exponential function, things that grow exponentially. You've heard that phrase in everyday life. We also have its inverse, which is the natural log function, logarithms. Okay? These are two functions that we will study in much greater depth spring semester. And then the last one is something called the logistic curve. And a logistic curve helps explain a lot of real-life phenomena. So if you think about certain populations, like a deer population only gets to a certain point before it starts to level off because of resources. Certain sorts of viruses and infections spread in a way that is common with a logistic curve. Again, I just want you to see it so that when we study it later, you've at least seen the picture before. You are not responsible for its domain and range yet. All right, so the parent functions, learn them and love them because they're going to be around for quite a while. The sooner you can get those pictures into your head and understand their domains and ranges, the better you will be for the rest of the year.